So when you introduce randomness to a system, by its sort of very definition, if you were to do 10 trials or 15 trials or, some sample of the population, every time you do it, you would see slightly different results. So similarly in transportation, if we were to go out and observe an intersection, we wouldn't see the same thing happen in the same 5-minute period one day versus the next. So one of the things you can do is set up simple simulations in Excel. So you're probably familiar with the random function in Excel. And so if you're not, anyway, you just use the function RAND, and what it does is it generates a random number between 0 and 1. And so there's an equal probability across that distribution. Well, when you're trying to model things as an exponential distribution, and you have a mean value, you have higher probabilities around sort of the average arrival rate, or the average or the expected value of the headway, as opposed to sort of the tails of the distribution. So you can convert so you can use the random number generator to convert it into a function that follows the type of probability distribution function that you want. So this isn't a class in statistics, so I won't get into it too much, but you essentially back solve. So a probability distribution function has the probabilities are between 0 and 1, the same as a random number. And so you can, instead of solving for the probability of an event, you use the random number generator and you convert it, or you transform it so it's solving for the headway. So anyway, we had that exponential distribution, which is why you see the sort of natural log as being the inverse of the E function. But anyway, so if you look at this value, what I'm doing here is I've set up a 15 sample simulation of how vehicles would arrive and how vehicles would depart using random using an exponential distribution. So what I've set up here is an arrival rate of lambda of 6 vehicles per minute and a departure rate of 10 vehicles per minute. So it fits our assumptions for our MM1 model, and that the arrival rate is less than the departure rate. And so in here, all I've done is the formulas over here are just taking those values and looking at how many, instead of vehicles per minute, vehicles per second. And then here we have the average, right? This is just the lambda value, and the mean. So the expected headway would be a vehicle, about 10-second average headway between vehicles. So, and conversely, down here for the departure, it's just pulling information from the 10 vehicles per minute, which we would have an expected mean headway of 6, right? So a 6-second headway in terms of the departure. So here it's just it's taking this random number generator and sort of back calculating for headways. So what we get is a distribution of headways that follow that exponential distribution. And if you're not familiar with the random number generator, anytime you do something in an Excel spreadsheet, it just regenerates. And so you can see every time you hit enter, what's happening here is we have the average headway of the sample. So what's happening with these 15 observations versus the mean headway of the distribution or the population that we would expect. If we had a large enough sample, we would expect it to converge on this value. And sometimes you can see the values drift further away than others. But if you did enough sort of trials of this 15 sample, you would see that they really converged around 10. Similarly, if we did more than 15, if we did 150, then the likelihood that this value of the sample looked significantly different than the population would be pretty low. So one of the things that you can do with this is then you can kind of create these simulations of what it would look like of vehicles arriving and departing. And so we've been seeing a lot of videos of the simulation software. This is exactly what it's doing in there. It's looking at the averages, and it's running sort of simulations. So you see that random kind of noise that you do in transportation systems. So over here, what I've done is just done a static copy of it, because every time I hit enter, I get new numbers over here on the left side, and I wanted to sort of hold those values constant so that in the next part of the video, you just look and see what it looks like to see random arrival headways. And so I put this spreadsheet up on the course Blackboard if you're interested in how sort of simple simulations in Excel work. But mostly I wanted you to see these numbers here. So this was just one trial of modeling random arrivals that had the 6 vehicle per minute arrival rate and the random departures that had 10 vehicle per minute, and these values that you'll see in the rest of the video. So normally, if we were in person, we would bring up this spreadsheet and kind of run a trial, and then I would have asked you to move around the classroom and sort of simulate and see what happens when you introduce randomness into the system. So the big takeaway here that you'll see in the videos is that when you add randomness, there's certainly a loss of kind of capacity. You see queues build up with the introduction of randomness that you wouldn't see under uniform arrival. So one of the interesting things is thinking about, well, how can technology help us in this way? So a lot of the capacity issues we see at, say, a signalized intersection or a metered on-ramp is because of the randomness of how people are arriving. And if we could use kind of connected vehicle and vehicle communications, we could get people to arrive when there's capacity in the system. Why we see queues when we have arrival rates that are less than departure rates is that there are times in the system that there is no one. So like kind of back to the park booth or the toll booth operator, there are times when there's no one for that operator to serve in the system, and that unused capacity cannot be sort of banked for a time when you have a queue. And so the randomness and not being able to meter people in is what causes the queues to happen. Okay, so modeling uniform arrival with a person entering the system every 10 seconds and a departure rate of 1 person every 6 seconds. So as expected under uniform arrival, because uniform system, since the arrival rate is less than the departure rate, no queue forms. Okay. Okay, so now we're modeling the randomness in both the arrival and departure rates, with the average or expected value still being the same as in the uniform of 1 person arriving every 10 seconds and 1 person departing every 6 seconds, but now we have randomness in both processes. So let's see what happens. So we see the queue starting to form, and we see the wait times get longer. So even though the arrival rate is less than the departure rate, we see the keys form that we didn't see under uniform arrival.